Right, okay, so we've got a live broadcast going. Let me just hit the refresh button on and in the chat. I'm just going to put a test in our chat. So just go to the live studio and I'll hit test. Right, so that's all working, and this session today is looking at Google Colabs, a popular resource, I guess. I wonder why the text is always so small on this. Let's just have a look here if we can Control plus it in this one. Okay, I can expand it this way. So we're going to look at the Google Colabs, and I actually set a section in here. So our section will be, I've got Colabs here, and did I just do Open Colab, Deeper Dive, maybe Browse Notebooks? I went to Browse Notebooks actually. This is a section, Machine Learning. There's there was different things, but actually I will go through some of this stuff. But some of this code actually doesn't work, which is rather disappointing because it all looks quite nice from Google. And then they give you these worked examples, and I tried 2 or 3 of them, and there's various different reasons that they don't work, and I'd have to troubleshoot to get them working, which I guess that's not the point of an example. You kind of want it to work. I tried this Twitter pulse checker. On Google Colab, you can't try too many things at one go unless you've got a paid for subscription. But then I kind of gave up and went for something I think a bit easier. Where was it? Data visualization. I think it was this one. Explore patient database with machine learning. It could have been that one actually. But anyway, it leaped me onto this, so I thought I'll have a try of this one. Media API, images, videos, da, da, da. So this is quite nice. I came across this, which is new, which is this media API, and I'll have a look at what this actually does. So it reads, writes, and shows images. Actually, it says it there, and videos in an IPython Jupyter notebook. So kind of like went over there and sort of like did a pip install to see what it is, and you know, that's what it pulls up, and it gives you a worked example. I guess there's a home page anyway. It's the same worked example on the home page, so there's not much to see there, I guess. But anyway, let's. I'll keep that tab open just in case. But scroll down and sort of like I've run this piece of code here. All that does is, or on any log, but I run that. Let's just run it again, and let's like run this one. Right, and then I run this piece of code. It doesn't do. It's not doing very much, right? mp.randomseed to NumPy. We've imported NumPy from up here. Creates a random seed and then media, resize it. Right, it's just an image. I guess it's 50 by 50. You know, we can have a muck around with this kind of stuff, like turn it to 100, so maybe be wider than longer. Run it again. Oh, longer than wider. So this is the vertical, and so over here. Right. This is okay. Resize image. If I hover over it, okay. So we've got the actual image itself, which is an array. So that's how this works. This is an array, the first argument. And then it's, so this here is the image. And then this is a, I'm wondering why that, and then this is going to be a tuple. Or is it, so not, is it called tuple actually, or shape? So we know we actually got there. So end shape is, I wonder actually if it says int. It doesn't, we do it by inspection, but basically shape vertical by horizontal. It goes this way round. Let's just, so if we wanted to make it wider now, let's do 200 that way, stretching the image that way. So we're just resizing an image basically. If we do it by 10 by 10, we'll have something small. So let's just go back to the original. We'll just do 100 by 100. I guess that's decent. Okay. And on top of this, I wonder what happens because it's got border equals true. I don't know, like, is there like a border thickness or something? Comma. Let's have a look what else there is over here. Media show images, input on random, args, keyword args. Doesn't really show what the keyword args are. So maybe, I don't know, can we see somewhere what options that we've got? Like if we can make a fatter border, for example. No. Sometimes these things are a little bit annoying because show image kind of, because I want to know the use case. How do we know the use case? Maybe, I guess, like if I try and make another cell here, is it help and then object media dot show underscore image. Let's see what happens on the help on that. No, because it says the same thing as show images. It's got a GitHub here, URL GitHub. Oh, there was actually some stuff on that over here. Well, it's got a size, CMap. I just wanted to make a thicker border, can't do it. Okay. Not sure that that was what I want. Okay, that was just that's just the URL of the actual image. Right. Okay, we have to accept that, I guess. Okay, I'll leave that cell there. But it doesn't show very much on it. Border equals false. I hate the fact that the IntelliSense is a bit slower, which is why I use VS Code compared to Google Colabs. But there's no border, and with border, it wasn't that much difference. In fact, I wonder if I can do both. So there we go. Can't even tab. It's annoying. There we go. It's just slower. The IntelliSense is just a bit slower to pick up. You can barely see that there is a border or not a border, but whatever. Okay, let's comment this out. And read image. Right, I don't know where that image is from. Have we actually loaded an image from anywhere? Because, I mean, okay, yes. So basically, you can have an image or a local path. That's basically, this is how you get it from GitHub. So I could actually, I wonder if I can follow the link. Follow link. It'll open up a link on new tab. No, link's not found. Because basically, I wonder if I stuck this bit at the end. Copy that. Paste it at the end. Not sure the raws will necessarily work. Oh, they do work. Yeah, there we go. So that's the actual image. So it's the same image as before. So yeah, I better post this actually. I'll tweet this one. YouTube. I'm just posting this on, so it's the same image as before. Oh, horrible! Don't want to do that. Twitter. inspecting Google Colab. There we go. I don't know if we'll get comments or not. Never do really. Sometimes do. But we're just going through on this. Likewise, I guess we could put this MP4 into the actual video, but all of this is a location of the path. So print. There we go. I think we're okay. Let's just comment this one. There we go. Just wanted to make that shorter because I wanted to just keep that in there. I'm not going to run it. Just what image.show does. It's kind of like the docs for it. And okay, so we can read our image. Image2 equals media.read image, and now we can do things to image2. So we can add a title to it. Okay, fantastic. Again, this image.show doesn't give us that much. So I wonder if I hover over that. No, just trying to see if I can get the keyword arguments. Okay, so here's what I'm going to do, which is over here. What are the quarks for media dot show underscore image in Python? I better copy all of that because I'm not sure that just and that bit over there, turn that like that and run. There we go. Let's see what happens. It's explained to me what quarks are. Right, because I wanted to see what are the capabilities. What are the docs for There we go, for show image. This one. Okay, there we go. Interpolation, CMap, alpha, weight, window name. Okay, so there are some things there. Okay, maybe it seems to follow OpenCV, PIL and Matplotlib. So maybe we can just ask a question if we want to do something to it. But if we've got title, size, we've tried interpolation. The interpolation method to use, I'll just over here, the interpolation method used if resizing common values nearest. Okay, how to use CMap. Right. On the side, because we might just have it there anyway, because these are some, I guess these are just some examples of what can be done. In fact, there is over here because we've already got the CMap. So this is going to spit out something that's kind of like image CMap equals CMap. So it's very Matplotlib-like here. But then it might be different color maps and so forth. Let's have a Right, image streak, media.resize image, okay. So we resize the image to a 60 by 60. And this is just np.random. So again, this is just an array. I guess it's 5 by 5 of random numbers. I just want to do here. Great. Copy that. Paste that over there and then print. Wait for the IntelliSense to wait all day. Print array. So the first thing that we'll get is the array, hopefully. There we go. Okay, fine. This is basically an array of, yeah, it's an array of arrays. So there's five across and 5 down. Okay. Don't need to print it out then in that case. Well, actually, okay, fine. The reason why is because I presume that this is going to be centered around 0. So over here now, I could print out the array, but basically this is the array over there like that. And the same thing. But let's just make this 200 by 200. There we go. For human visibility. And okay, that's fine, you know, and if we were to change this, I guess if I made that 0.9, did it do very much? No, not really. 2.5. How about 2.5? There we go. Just because it's a random numbers between 0 and 5. Let's have a look. Still doesn't do much. 20. Okay. Let's just run that, leave that there then. More examples of color maps and value bounds. So, put that there. Close that one up. The top one here. So what actually happens is this is a dictionary, and the dictionary contains the different titles, effectively, or what the actual different images are available, and then this page that show images shows all of this dictionary of images. Although that is a dictionary. So the first one is a string, and then the second one is an any. And this anything here is the actual media to be shown. So I guess this is what image 3 was anyway, which is this grayscale. And that was the original image. And then 0 to 1. So to RGB, image 3, Vmin, Vmax. Okay, I think that's basically scaling it. That's where the color map BRW. So there's different color maps. So there's a different color map here, which is jet. And then this is jet, color map jet, but it's scaled. If we do Vmax equals 0.9, for example, I guess this will be closer. If we do 0.1, let's just have a look at it. Yeah, do we see that one? It became quite. So it's actually Vmax was. This becomes sharper. So if I make this 0.9, it's very blurry. So that's what that Vmax bit does. This Vmin and Vmax. So if I do 0.8 to 0.9, I wonder if that sharpens it again. No, it doesn't. It just removes everything. Okay. 0.2. Right. 0.1. Looks like it's eliminating stuff basically. O. Right. So as this one goes down, so 0.6. Right, we're getting to see more 0.5. What I'm looking at is What I'm is this bit over here. I'm just looking at this one. Every time I rerun it, keep it in the box. So every time I change that number, it gets sharper. So 0.4, it's still sharpening up. And if I do like 0.3, 0.2, 0.1, 0.1, super sharp. Okay, you can see like all of the greens are basically left, and so 0.1, it's about right for a very, very sharp image. It's basically looks like it's all like taken this and this area here, so it's kind of like this area here has become this over here, and then this area here has become this over here. You can see the sharpening of it, basically the same over here and over here. And if we were to change it back, so 0.9, we get this blurriness on those images, and it's kind of, that's what it is. So let's get rid of those because we don't need them. So write an image to file. Don't even know where this will actually go. So file, save a copy in Drive. Okay, I don't want to write the image to file because I don't know where it will go exactly. Somewhere in my temporary directory, I guess, but where? Don't know where it's gone. Maybe I'll have a look at a Google Drive. So, okay, Google, that's Colab. Let's have a look at the old Google Drive. And let's go back, and image3.png. Well, it hasn't made it here, so I don't know where it's gone. /temp. So is there a temporary folder? No. If we hit refresh on this, no. So I don't know where it would have actually gone. Pull this out because I don't need it there. And maybe I'll try and do a search for it. Image3.png. So if I take this, just see if it's gone onto my drive somewhere. Find it. No, it hasn't. Oh, hold on. I've got an image3.png. File information. Organize. File information. Details. I do have something here, but that doesn't really look. Image3.png. Okay, it won't be that one because that is just this little image here, which is nothing to do with that image, so it's coincidentally had the same name. So it's not in any temporary folder either. I could see the path of it because you can see the path in it. So okay, I'll just get rid of that. I guess if I was, I presume that if I'd saved this a copy in my drive, they would go in a drive. So I don't know where this version of it has actually gone, which is a bit of a because then if you're always saving write image, where's it actually writing to? If it's not on your drive, is it in the cloud? If it's not in your storage space, is it on Google's? Does it get deleted? I don't know. Video images, video examples. Display a video, a 3D or 4D array of an iterable of images. Okay, so there's 10 images here, and it's going. I guess it's going to play them. But what are the actual images? Moving circles, right? Let's just run it. I don't get where this moving circles is from. Let me just do a control find. Moving circles. Where's the other version of it? It says 1 and 2. Is there another moving circle somewhere? No, it's the only thing that comes up. It says 2 of 2. But this is moving circles. Show a GIF so that it is visible in the GitHub notebook preview. Okay. I mean, if for example I made this 20 and reran it, okay, there's 20 circles, but like, why is it going that way? What's the 65 by 65? Let's just say that is 5 by 65. So we're going to have a smaller. Okay, so that's the array again. Okay. There we go. So it's a little bit clearer now. Okay, you know what I'm going to do is I'm going to lazily take that and put, what is this? What does this do? Question mark. And paste that in there. Then in paste variable, whatever. Let's get it going. Okay, so it's a function that you showed seems to be generating a sequence of images, images with a moving circle. That's a starting position. Is likely specified as start. But this is from the media, right? So it's a bit annoying. Okay, basically this comes from here. Generates a sequence of PIL images moving across frames. The first argument specifies the center position of the circle in the first frame. 6 frames, the circle will move by a random delta x. Okay, fine. Is that what it's doing? Right, okay, fair enough. It's about understanding what's going on, because it's really annoying. Right, so it started at 100 by 100. No, that just doesn't look correct, because that looks like the size. Because if I made that 200, it's going to stretch it vertically. We know that, right? So that's not the starting position. So maybe I'll do something like Let's do a copy, paste that in there. It's going to send me back here. I mean, that's this particular one, you know, that's the one that we've seen. Show image, show videos. Okay, here we go, show videos. Right, that's a bit better. Now we got the docs because we can see some of the stuff that's here. So we are using, at least in here, if I scroll back down to the actual videos, this moving circle, I'm going to move this over here. That's show videos. So I'm going to go to moving circle. There we go. It comes up in 4 different places. Moving circle, shape, number of images, 60. Right, def moving circle. Finally we get there. Right. So it's just a shape, an int, and the array. Okay. Returns a video of a circle moving in front of a color map. That's all it's doing. Okay, fair enough. So it is as bland as that. We have no control over any of the other bits. 200 by 200. Like it, I guess like we don't even have control over the height or anything because there's no like keyword args or anything like that in here. It's got a star in there. I wonder if we can muck out. Sometimes I find the documentation in Python a little bit annoying because you feel like you want to do more or there's more there because I see this little star over here. View source. Star. Right, so this is the actual definition of the function here, like its signature. So it takes in this tuple. It looks like it defaults to 256 by 256. If you leave it blank, it has a number of images 10, and then it's got just here star. So it's interesting, but that's all it is. Check do shape, do type is, and do type. Yeah, it looks as bland as that. I don't think there's anything more to be done with that. So okay, fine. Show images, video 1, column 6, border true. Okay. Where is video 1? Video 1 is this. Okay. So this is video 1 as well. This one here, interestingly, I guess, is there more than, because I did 20, 1, 2, 3, 4, 5, 6. Yeah, it's 26 by whatever. I'm going to make this border 5 now. Columns 5. Because then you've got 5, 10, 15, 20, so we can kind of like see it here. In fact, yeah, this number here, this is contingent on number of images. So if I set number of images equal to 20, then num images equals number of images, then this here will be num images by 4. There we go. Same thing. Int go. Probably because I didn't run this one. How about that? Run it. And then run this one. Because that wasn't defined. So it's actually safer to do the integer version anyway, because columns equals, and then it'll be right. There we go. So that if I made this one, wherever it was, number of images, so I make it, and that's always got to be multiples of 5, 25. I have to cheat myself now. I don't even know what this will do. I will still put the extra one. Okay, but it appropriates columns, so it's a bit nicer at least. Right. Show images. Okay, show the frames. Now here's an interesting one. Video 2 is read this other video that was there in the beginning, which was this one here, this video.mp4, which if I navigate to the link again, follow link, and then I append this link with video 4 like this, that's actually, oh, okay, so it's tried to download an image, fine. I have to go to my download somewhere and play an image. Downloads video 4. Okay, play. Well, it doesn't last very long. It's like 1 second. A 1 second clip is what it is. There we go. Of a streaming river. So that's all we get. I'm going to hit delete on that. Delete. Guess we won't need that site. Doesn't do very much for us. But that's a 1 second clip of that river that's flowing, and which is this. So I guess we can resize it. Frame rate. So basically it's controlling the frames. I guess if you're making like a video app, that's what this will be useful for. And right. Shape is, so whoever wrote this now is giving us a little bit more clues at least as to how it works without us having to go to the docs. But number of images, okay. So it's 10 images, 180 height, 320 width, and what's the last one there? Number of channels, 3. I don't know what number of channels means. Probably red, green, and blue actually. Must be red, green, and blue. So then we've got the frame rate at, I guess that's the defaulting frames per second. Resize the video. Video shape 1:3. I wonder if we turn that to like 1:4. What actually happens? I'll go back to 1:3 because I didn't actually run that to test it. Okay, that works. Maybe that was out of bounds. 1:2. No, it doesn't like it. Shape 90 is not of the form width height. Okay. Oh, I see. It's take this shape here. Is this, and its elements 1, which is, this is element 0, so it means elements 1 and 2 by not including 3. So the shape is these two bits here, which is the because we can actually print this out. Print that. Yeah, we see it's the 180 by 320 over there. That's that, like that print. That's what that is. So that's fine. And then divided by 2. If we did divide by 1, is that going to give us the original shape? Yeah, it's just a bit bigger. So divided by 4, we'll get this tiny image. Okay, so divided by 2. 1.5. Doesn't like it. Presumably it needs to be an integer then, and that wasn't an integer, so 3. Smallish again, right. Okay, we'll just halve the image size. And frames per second. So, less frames per second. Do we see it like being bittier? Yeah, there we go. And if we made it 20, I guess it'll be faster. A flowing river, there we go. Way. So there are different options. That's what we can do on with the media play example. So this is just basically, I guess it is actually an example of this media API, like the usage of how this can be used. Basically, look, it's reasonable. It's something that goes into a Colab notebook, basically, or a Jupyter notebook. So let's just run this one as well. So we've got these, again, mirror loop, so that's just going to keep on looping, I guess. This bit here, -1. Does it go forwards and backwards? Yeah. So we've got video 2, and then video 2, which is an array. List, it's reversed. So then we've got this next one, which is roll, color map. Okay, so this rolls down, and this one's a fade here. So we see each one, because basically the mirror loop goes here, and the roll goes over here, and the fade goes over here. And they're basically the 3 things from this dictionary that feed their way into this media.show, and media.show is effectively all of the items in the dictionary. So these 3 things here, they're all the items in the actual dictionary. Okay, this one's a nice one. I've still got it playing actually, because I started that right in the beginning, and I was mucking around with this. So I just wanted to make this like some really big number and like test it, because the original was 16, and then I stuck in 1,000,000 and broke the notebook. So basically, I think this show video bit here is it's repeating itself after every 16 cycles, and I was like, well, let's try and move that to 32. Right, so it's going to last a bit longer, 64. So like keep doubling it or whatever. And 1,000, make 1,000 cycles. There we go. I won't do binary numbers anymore. It's a bit annoying. But you see 1,000 takes 1 second there. And so 2,000 will take 2 seconds, roughly. And 10,000 will take 10 seconds. So when I put in 1,000,000, it probably is going to take 5 minutes to generate it. But this will run, I think that this is now going to run for 10,000 loops, iterations. What would be interesting is actually to print the step that we're on, and then clear. So what I want to do is do this. How to print a line in Python, and then it's probably not the right way to actually do this, but to ask it. That's what I was looking for, something like this. I wonder if I can get this. I'll just do this up to 10. Well, that's just media.show actually, so we'll never see it. So I want to print the line number. So I don't know like what iteration that we're on over here. But these are all Conway's Game of Life. Conway was a mathematician. It's really interesting actually. But basically we start from some random point. This one's actually reached a steady state this time. Sometimes that happens, so that these are like stable points. But basically there's rules for the Game of Life, like if a piece has got like 3 pieces next to it, it stays alive. So these ones always stay alive. So you get these like patterns, and these ones are called, I think, oscillators or something, because they flicker. And likewise here, and then you get like guns and things. So if I rerun it, so we saw last time when I ran it, like, or at least it was always running the whole time when I was doing it. It never got into, sometimes the Game of Life gets into like a stable state. So the last one we saw was a stable state, and this one is, it looks like it's a perpetual state, because so long as things are moving, you get this perpetual state. And yeah, so this one might go on and on and on like the whole time, and it was before, like it, however long this like YouTube thing was going on for, which was like 40 minutes. That Conway's Game of Life was just running and running. So, and it's got to get through. Well, I can't remember. I don't know if like I did 2 to the power of, I can't remember what it was, but like I think I did like 100,000 or something like that. And each one of them, well, frames per second is 8 frames in a second. So you can actually work that one out, because we've got 10, as in how many seconds will this run for before it loops. We've got 10,000, and then we've got 8 frames. So is it 1250 seconds? So that is divided by 60 is 20 hours, minutes. I think we run for 20 minutes, this particular one. So if I had it for longer, it would run for a couple of hours, like in perpetuity, basically. Mandelbrot, that's going to be interesting too. Let's just get this one going anyway. That's just the seeds, I guess. Again, everything here is, this is a dictionary comprehension. F seed next iterable tool, full seed in range 10. So this creates a dictionary of 10 things here. So seed equals and then the number. So 0, 1, 2, 3, 4, 5. So it does 10 of them here, 0 to 9. Starts it. And remember that we start at 0 and go to 9 in our range, and yeah, and then we just pass it in, I guess. So that's all of them, and it's the 100th generation of each one of them. So with the different seeds that are available. I wonder if we run it, we always get the same seeds, don't we? I never okay, the whole thing about this seed stuff is, I guess it's so that you can repeat it. So it's random, that you can repeat code. But I guess if I was to do, Well, we'd need to go back to our game of life here, I guess, and kind of like not use the numpy seed, but just use like time. If I was to take this out and then sort of like place it here and then do that and then do, I'll just put that there and just run it. Right, how about printing it then? N equals, right, and then N. Okay, print N. There we go. Okay, we've got a none there. Right, okay, well, I've got a none. Oh, because that's just a seed, isn't it? Okay, fine. I guess so. That's a seed that actually generates, that creates this random, in theory, that generates this randomness. And here I'm just going to nick this shape, which is this shape here. Right. Yeah, okay, fine, it should work now. So I'll say N equals just going to be a bunch of random numbers, though, I think. Yeah, okay. Between, but the thing about it is that that bunch of random numbers is always the same. So I don't want that really. I want this seed to be if imports time times by something like time dot time. I don't know if that will. I don't know, because that's still going to be the seed, isn't it? Yeah. I think. Well, I'd rather just do. I guess there's other imports. I won't go into the NumPy. I won't go into the NumPy imports actually. So, or at least the NumPy randomness. I could do. Oh, you know what? Actually, random numbers with NumPy. Generate random numbers with NumPy. Without using seed. The seed is randomized implicitly. Okay, but I think if you've set the seed, then there's random state. Okay, range equal. Right. Okay. Yeah, that's what you want to get. I guess range equals random state, leaving the seed unspecified, initializes it randomly. Okay. So basically, I think I'd want to remove the seed or not run it with a seed in there. Because if I did, then these here would always be changing. Now here, that's based on this with this seed. If I just said I could. I just wanted to change those images, but okay, we'll leave it like that. That's just how it works. That's just the 100th version of each of those, which I guess is fine. Finally, we do Mandelbrot. This one's quite a good one. I've written about this in the book, actually. The book, one asks. So let's just go over there and then do look. Drag it over here. This book here, which is how to improve your ranking and become a better programmer and a lateral thinker. Although Stack Overflow rankings now aren't, it's got 5-star rating. There we go. Stack Overflow rankings aren't what they, or at least they're going to go down because everyone uses these. Everyone's using these general purpose transformers. The one here that I'm using is Claude AI, but I've got a whole ton of them open, or not open. I haven't used this one for a while. This is Bard. Do quite like it, but I've just started to use Claude AI. So, I mean, Google Bard's fine too. The original one is ChatGPT, which is this one over here, which I'm just kind of like launching up. I'm going to log in, sign up, ChatGPT. Probably actually, funny enough, continue there. Like password. I wonder if I can continue like that. Can do. Okay. Polygon sides. There we go. Oh yeah. Okay. Right. Vectorize row optimize. Yeah. I mean, it's sort of like clear as well. That's GPT. I'll close it out. But this one here is quite nice, so I've kind of like tended to use that. You know, they're all competing ones. Yeah, so we don't necessarily use Stack Overflow anymore, but nevertheless, great book 3 because it contains this Mandelbrot set, and it goes into it until it shows you how to do it. But we've got it over here anyway. So visualize a divergence of Zi in the sequence Z0 equals 0. This is the modulus or the it's complex numbers basically. So the norm space of the complex numbers, and Zi plus 1. So the next complex number is, so that these are the, like, imagine that's the axis over there. I'll draw the axis. I think we can see it anyway. Don't need me to draw it. There. My badly drawn version of the axis. There we go. But basically, well, actually, I will do it. That's the axis, and I don't know where. I can't remember where it was, but it's sort of like complex numbers. This is like the real. These are your reals here, and these are your imaginary numbers. I don't like to call them imaginary numbers. Right, you've heard it here first. These are your orthogonal numbers. There's nothing imaginary about complex numbers, and there's nothing complex about complex numbers. These numbers here are what we refer to as the real numbers on our number line. They're the numbers we know. And these are just happen to be numbers that don't lie on the number line. They're orthogonal to the number line, but they still exist. So that's what a complex number is. But anyway, finding that gives you, like, you know, I guess complex numbers so quite effectively moving are circular in nature. And some Mandelbrots. Okay, we'll have a little play with this Mandelbrot. So let's just run it, make sure this one's running. I presume it is running. It's in the state it was in. But then we can do things like I wonder if we do 400 what happens. Let's have a look. wanted to put two Mandelbrots next to each other, which we can do, because I can do a copy cell. Where did it paste it? Don't know. Don't see it. I wanted to duplicate a cell. Copy that. Paste it straight down below. Paste it there. 200 for the purpose of comparables. And like we can see that this one here, which has got 400 iterations, is just finer than this one here. I wonder if you can stick in like 800. I keep on doubling it. It's always the safest way with these things, because I'm just wondering how long it actually takes. It's taken 2 seconds to do it. We can see like this blue over here, and this starts to disappear. So we just get this like level of accuracy. Can we zoom in on it or anything? No, we can't. No, okay, that's not zooming in. That's just me zooming in on the entire code. I wonder if I change that to a 3, what will happen? Will we crash or will it work? Okay, fine, works. But yeah, we can just do various bits, but this Mandelbrot set always kind of like effectively looks the same. N equals 4. I see what it's done. You see this curve at the top? That's what it's done. Like the active area, I think that is. Yes, just made it wider basically. So yeah, that's kind of like, I guess basically it. That's Mandelbrot. Well, there's not much. See Wikipedia. Leaving Colab to go to Wikipedia. It's kind of like what happens when you keep on zooming into the Mandelbrot set. So we see here, this is what's created, is a two-dimensional set with a relatively simple definition. That's the beauty of it. It exhibits great complexity, especially if it's magnified. It's popular for aesthetic appeal of fractal structures. The set is defined in the complex plane as the complex numbers. So this is what Z is. It's easier to show it in the images than me doing it, but these are the real numbers here, and these are the imaginary numbers or the orthogonal numbers. And our complex number, our new type of number that lies on this plane, is now made up of this real number, the real component here, which is A, and then this imaginary or orthogonal component. Now what is this? What is the axis here? The axis is I, basically the number of units times by I. I is the square root of -1, which is why it doesn't exist on this number line. So it's something that is on our real number line. So our new number is made by something that lies on our number line and something that doesn't lie on our number line, but still has a mathematical meaning, because we know that I squared is -1. So this bit here, and if I can do that all at the same go. No, I can't, because it's now in the drawing mode. Let's get it on, complex numbers. This bit here, this I, if I square it, imagine that A is 1. I squared would actually be over here, be -1. So that's kind of like what it is. Yeah, and there's lots that can be done and so forth. So this was published, the first picture published of the Mandelbrot set in 1978, because it was a dot matrix printer, and like although you could like imagine this kind of stuff, it wasn't really imaginable to an extent, because also it wasn't showable to the world in 1978, because the only thing that this dude had was a dot matrix printer, basically. At best, I imagine, like, here's these little stars or whatever. That's the best that could be done. But now we can like go into these things like tens of thousands of times. So it's all these different features and characteristics and so forth, and the mathematics is humongous on it. So what we get here is kind of like a first level view of the Mandelbrot set. Right, let's have a look here. Image rate distortion. The one thing that's nice and not nice about Python is, you know, it's supposed to be readable, but like it's kind of difficult to like read it like in live terms here. This is a for loop for param in params. It'd help if there was a bit of commentary somewhere in there. I know that you're supposed to leave the commentary out, but is it really that readable? I guess we take an image. So images is this blank dictionary, and okay, params is a bunch of params. I don't even know what they are necessarily, although it looks like they feed into here. So okay, that's what they are. Well, you've got this random you've got this blank dictionary, and then I guess we're going to populate the images dictionary with a whole bunch of images. I wonder if we can make this quality better than 100. Let's just run this just to make sure that it works. It is working. Okay. 200. I like to break these things. Am I only, it looks like I'm potentially only just changing the title and nothing else. That's the thing, I don't know params where it fits in. Can I find params down below? There we go, for param in params. Okay, so really I'm looking for param. It is doing this compression. Quality equals param. Let's just let's just look at this quality of this one here, this end one. So basically we're looking at the quality of this. I wonder if it changes between a run. So I'm going to run it now. Keep an eye on it. Doesn't look like it's changed very much, but maybe that's the original image. Maybe it can't get better. And remove that. Just rerun it. Video rate distortion. Just doing some running there. What's the epilogue? Okay, I think it's probably enough. The collab was acceptable. This particular one, at least it worked when I said it was acceptable. I wonder if you could file exit out of it. No, you can't. I'm not going to print it or anything because it's kind of like just there. Close that one out. Go to collabs. I'll go to a fun one. I wonder if it is fun. It was now loading this notebook. Every time I open one of these things, I get a different type of error. So I'm not seeing this error. Notebook not found. There was an error noting. Ensure that the file is accessible and try again. Authorize. Okay, let's just go to Google Colab like that and open Colab. I didn't want to do it that way. Okay, so Google Colab. I'm going to close all of these up and browse through the notebooks again. And I wonder if this time, if I do click on it, Advanced Python tutorial. list comprehensions, lambda functions. It tells you, okay, fine, well that one's working at least. Can't go back on that. It just launches it somewhere new, basically. So we don't need this media API. We broadly understand what it does. Or go back on this fasting and try to launch it again. Loading. Yeah. So some of these things just throw error messages. I could go through and debunk it, but I'm not going to. Physics simulations, that'll be interesting. Does it work? This one works. Some work, some don't. When I try to run them, some do or don't work. So a differentiable physics engine, BRAC, simulates physical systems made up of rigid bodies, joints, and actuators. Okay, this is quite nice because I see here a state t+1, and it basically is based on the previous state, which is Mandelbrot-like. We like these things that evolve, basically. They're the dynamical systems. It uses JAX. I didn't do a video on JAX, but I did have JAX actually open. I think I've got it open in one of my other tabs somewhere. So, or maybe I don't anymore. But JAX is a bit more powerful than NumPy. So, and in fact, here on the next line, from JAX import NumPy as JP. So JAX kind of like is a wrapper around NumPy, and it lets NumPy work in the GPU and TPU. And I think that's the advantage. That's what JAX basically does. It interprets all of the NumPy stuff properly into TPU's faster processing. So state is a dynamic. Anyway, we'll go back. System. What is system? The static description of the physical system, each body in the world, its weight and size, and so on. Okay. T is the time, each position, rotation, okay. And act is dynamic input to the system in the form of motor actuation. Okay. I see a try to import Brax. That's going to be fun. Accept import error from IPython clear output. Okay, so it's going to try to import Brax this way, and if it doesn't, if it gets an import error, it's going to do a pip install of Brax this way, and then import Brax. Okay, and clear. It does a clear output as well. Nice. This notebook was not authored. Yeah, I can run this anyway because it's safe. Connecting. Initializing. Python 3. Connected. Boom. We're in. It's running. Right. It's looking like it had to do all of that importing stuff because look at all of that going through. So nice and slow. So it couldn't do an original import of Brax, so it had to, from IPython, I guess, clear the display. And now it looks like it's run there. I should do something like print imports are done. Right, something like that. Anyway, bouncing ball. A Brax system is a data class. I'm going to click on that where it takes us to. Flax struct package. Okay. More Pythonic stuff that I don't necessarily know or do know. Well, okay. I don't know what an abstract is, or I did at one point, but I've forgotten. That may be constructed programmatically. Brax also supports creating systems using this and this. Too simple and intuitive physics. Seen XML formats. Okay, right. Let's click on one of them. There's tons of, like, we can go into this stuff for hours and hours. There's just tons of these things for the purpose of learning, depending on what one is doing. This is just absolutely humongous in the documentation. There's tons to do. I could play a YouTube video inside of YouTube, but I shan't do that. Let's just go back. Here we specify a board with radius of a half meters lying on the ground, the time resolution of the simulation in milliseconds. So that's basically it. It looks like it's, well, I guess it's taking this XML string here. So time step is that. Where's the half meters? I guess the size here is the half. Let's just run this. Warning, blah blah blah, no GPU TPU found, falling back to CPU. Set this one level equals 0 and return for more info. Crikey. I don't even know what that... Do I just put that in here? Oh yeah, okay. Right. Rack systems have all kinds of interesting fields, okay. Are we going to get a bouncing ball anywhere? That's what I want to achieve. Okay. Okay, it looks like we are going to, but let's have a look. Racks systems have all kinds of interesting fields we may manipulate or differentiate against. For example, the mass of our sphere follows 4/3 pi r cubed times by the density, where rho is the default density of this. So print ball link inertia mass, okay. And if we change this, or change our 4/3 pi r cubed, if we change our radius, for example, if I made that 0.6, it'd go up, this number went up to 904, so 0.5, because it's the cube of this value, whatever it is. So we visualize our ball like so, so let's just run this. This is using matplotlib basically. This would be a fig and a plot, but the figure isn't being used, so it's just plot.subplot, okay. Ball at rest. Tossing the ball. Right, so finally, to toss our ball, I've used these before. This is quite interesting because it puts these little things. So here you've got a slider. I was actually wondering how you get a slider. Just type it, type slider. And max min. So these are specific things in a Jupyter notebook at least. I wonder if it's in a normal Jupyter notebook, but it's definitely in the colabs. So I wonder actually if I did that, just like that, copy this, and actually went and opened up a, just go here and do a notebook, and I'll close this on the side and make it a bit bigger. But if I was to do that, print no, I don't get a slider in this one. This is an interactive notebook in, this is a Jupyter notebook in VS Code. So it didn't have an effect, whereas this same, oops, where was it? Well, this same line of code here has the effect of creating this, which is this bit here. and we see that this number 0.75, so basically this number here is based on like this slider over here. So if I go and move the slider, the number changes. There we go. And likewise the same for the other one just below. So this number here is based or comes from this ball velocity there. So if I move the ball velocity, it changes the value. And I presume that we can run it. I'll get rid of everything there. So let's just run what we've got. Right. Which is nice and slow. Still running. There we go. And yeah, I know. There we go. But let's make the elasticity more, or less, much less, like meaningfully less. Is it going to automatically? Yeah, it does. Okay. So now it's sort of like the ball. This is the motion of the ball. Goes down, bounces, and doesn't bounce much. So an elastic ball bounces a lot. I presume that this was probably loading, probably preparing the arrays or something like that. So this is a very bouncy ball. Let's make it with not much velocity. So negative numbers there. We thrown the ball up in the air. Yeah. Oh, it's going backwards. Okay, that's what that is. Let's get a 0. There we go. That's going to be an interesting one. Ball should just bounce up and down. Yeah, it does. Okay. So ball bounces up and down. Let's throw the ball a long way. And make it bouncy. Well, that won't do very much because we're throwing the ball a long way. We can see these executions executing 7, 8, 9. It's saying each piece that it's executing as well. It's interesting. Have I murdered it? Okay, there we go. That was a lot of time, 25 seconds completed at 12:01 there. So there's a lot of time to achieve not that much. Make the ball velocity less, make the bounciness less. We can see again it's kind of like doing its executions, and there we go. So like a ball, moving up and down. Triple pendulum. That's interesting. Connected. Brax links our bodies are connected to another by joints. Let's make the triple pendulum made of 3 links. This is a very famous thing. So here's our, I guess, do we have to run all of these bits? Must have to run each one. That one, that one. Create the arrays. And here's the triple pendulum here. So our pendulum at rest. So presumably swinging the pendulum. There we go. And again, it looks like we've got all of this sort of like motions and stuff that are going on. Initial angle, so that's going to be the initial angle. Pipeline, I don't even know what this pipeline thing is. Let's have a look. Step size, 1 millisecond. Okay. Yeah, we could jump the step sizes if it was. But they all seem to be milliseconds anyway. So we run this piece of code. I'm expecting to have to wait again. I guess computers in 100 years are going to be even better than this. So we'll be able to run this like much faster. The way that when you load games and things. I mean, this is basically the swinging pendulum. If we make the angle less, I presume that it will just redraw the chart. I'm hoping to do it relatively quickly. So yeah, there we go, and step size 5 milliseconds. So this is just a simple pendulum in motion. Don't even know what this positional thing is. I'm doing this by inspection, like literally clicking on it and seeing what the difference is. Right, there we go. That's an absolute mess. We'll leave that. That's cool. Right. We still haven't done the triple pendulum. Here's the triple pendulum. Pointing the pendulum. Because this one here is just, I think it's just one pendulum. Or is it? I wonder what this actually is. Run it. Let's just see what happens. Still running. There we go. And I guess if we change, this motion is random motion. We couldn't like repeat this basically. That's kind of like the key to all of this. I've just changed the angle. But basically what is randomness is this small change in number gives something that's, I'm not going to say complete, well, in theory completely, well it is completely different. It's an unpredictably different. So if I take this piece of code and I paste it down here, and this time I make this one just like 57 from 58 and run it, how different are they? No. Will it be predictably different? But I don't notice a difference because normally a change, let's change it to 47 to see if that makes, what kind of difference that makes. Yeah, I mean there is a difference. It's hard to see like the complete differences. Anyway, I think I might end it here. That's Colabs. It's got like a lot of features in it. It's got like tons and tons of stuff built in. This really is a massive space for data science. I'm kind of like, I don't even know what I was looking for here. Just really an overview of Colabs basically. So they go and give you some examples of things that you can do, and there'll be a ton more stuff. And that's kind of like really it. Um, yeah, I guess if you did like this, if you are watching it, did like it, or if there's anything that you want to say, comments on, be interesting to hear the comments. Definitely like hit the like buttons or whatever. 389 pages for the book. Yeah, quite long. At least you get value for money that way. Um, yeah, I think the link will be in the thing anyway. If you like it, hit the like button, subscribe, follow, comments. If there's something that you want to see, because I don't normally, well, I do. I do these like rambling things from time to time where I like just do overviews of stuff in kind of like just general exploratory stuff, and I kind of like just do it online. So yeah, let's see like people's thoughts on basically on collabs, and yeah, that's pretty much it. You know, I don't know if I'm convinced with everything, but you do get to use Google's GPUs and CPUs. I know that there's extra plans. Like one of the things that I saw basically said, I mean, you can upgrade here, want more memory and disk space. So there's things that one can and can't do over now. And I think that's pretty much it. So I'm going to sign out and thanks.